I've got a really apropos topic. I'm going to talk about GUI ducts. This is the Pacific Northwest Numerical Analysis Seminar. So you longtime Pacific Northwesterners know what a GUI duct is. A GUI duct is a clam. It's about this big. It has a funnel that's about this long. I mean, it's a hell of a looking thing. And there is no European language word for this particular clam because the Europeans didn't know about it, but the Chinese knew about it. The Chinese call it the elephant trunk clam. Boy, I didn't even put the right chart up there. I have the Chinese characters for a GUI duct even on one of my slides. What do GUI ducts have to do with scripted process? Anyway, about 10 years ago, we put together a little project at Boeing that was taking some experts from our BCA Aero Engineering group who were working hard on the aero grid and paneling system and putting together some tools for automatically generating CFD grids. And then we had a math group that was focused on some geometric modeling methods for multidisciplinary design optimization. And we were encouraged by our bosses to merge these projects into one, and we did that. And so we started this project in about January of 2006, I think. This project is now just about 10 years old. And these two groups that had struggled to see eye to eye a little bit on the right way of going about doing things continued to struggle to see eye to eye as we got this project started. And 3 months into this project, we'd made very little progress. And because of the disagreements and the bickering, and you can imagine. We were told that we needed to come up with a name for what this tool was going to be. And Roger Pomeroy, whom I know at least a few of you know, my two older Boeing colleagues for sure, but some of the rest of you maybe also, decided we were going to call this GUI duct. And we all got a chuckle out of it. I mean, we all knew what a GUI duct was. And the name stuck. And one of the neat things about it, the minute that we decided we were going to call this GUI duct, everybody started to get along. We had this funny, common, shared identity. It was a shared inside joke. And so there's a real interesting bit of sociology there that you really can form tribes with new people and find ways of getting along and coming to agreement on technical grounds just by doing something silly, just by finding something in common that you really like. So in any case, the GUI duct project at Boeing has been going on for 10 years. It has all of these features and highlights here that I'm going to focus just on one thing. We had intended this tool to be a really good tool for doing computer-aided engineering with. We were intending to come up with parametric families of designs that we would systematically explore the design space using optimization. And GUI duct works for all of those things. But along the way, we discovered that GUI duct was just, as the 787 program got into a little bit of trouble, we discovered that GUI duct was just the cat's pajamas for solving geometric modeling problems that arose in composite manufacturing. And so an entire engineering staff in Boeing commercial airplanes was put together called Scripted Process Engineering. That the purpose of the group is to take GUI duct and to take composite manufacturing problems and see what can be done about applying GUI duct to solve those problems. So let's talk a little bit about what GUI duct is. GUI duct is fundamentally a system for creating and performing manipulations and calculations with spline functions. In particular, tensor product spline functions. And so that is the basic the basic object. The AeroGrid paneling system from which GUIDuck is derived had about 59 different geometric entities that you could do computations with. In GUIDuck, we basically said, let's try to see what we can do with one. But we didn't quite make it with one. We ended up with about 10. But by far and away, the biggest and most important one is the tensor product spline object. It's implemented in GUIDuck in sufficient generality that it will model any old tensor product spline function with an arbitrary number of independent variables and an arbitrary number of dependent variables, including 0. So you represent points in GUIDuck as mappings from R0 to Rn, and you can get an n-dimensional point or an n-dimensional vector represented as a spline function. You can do the opposite thing. You can have 0 dependent variables, and then what you get is a mathematical description of a function space without worrying so much about what the range is. And it gives you a means of passing a B-spline basis around without any particular function attached to it. So this is the basic currency that is used in GUIDuck. And like all the CAD systems out there and any other number of other systems, splines can be used to represent geometry. So for example, if we want to represent a 2D line segment in GUIDuck, we can do it with the, okay, I've left something really, really important out. The scripting language. One of the things that is going on is that what we have done in GUIDuck is to add a bunch of spline processing commands to the Python scripting language. So you can write really tight, crisp Python scripts that will give you, do all kinds of really interesting geometry creation, processing sorts of commands. So we're going to start here with line, which will give you a line segment. But trust me, there is a flux command and a convolve command and all kinds of much more interesting and sophisticated things. In any case, the line segment here is represented as a function from the unit interval to that line segment, and you get parametric variation from the origin to 0.23, and proportionally you can implement points. So you get this function. Because it's a function, it can be evaluated, and we get the range, the image point of that particular function evaluation. And as I mentioned earlier, we can do points as mappings with 0 independent variables, or we can do curves. You can get surfaces with 2 independent variables. You can get volumes with 3 independent variables. With 4 independent variables, you could get a time-dependent volume. That's already getting to be a tensor product spline with 4 independent variables. You're pushing your luck there a little bit. If you're really brave, you can try 5 independent variables with a tensor product spline. But you even have 10 to 100 B-spline coefficients in each direction. And you see what's going on tensor product-wise with the combinatorial explosion. But GUIDuck can represent all of those kinds of things. And so one of the things that we can do, for example, if we've got a model of an airplane wing and we have a deformation volume that say, for example, is time dependent, then you could model airplane flutter by composing the deformation volume with the geometric model of the wing and getting a time-dependent model of flutter. All of those kinds of things are possible. Okay, one of the things that makes very experienced users of CAD systems very uncomfortable is that although you can use spline functions to represent geometry, not all spline functions are geometry. And so this metaphor of the basic entity that you're dealing with in the GUIDuck system as being bits of geometry that metaphor breaks down for all kinds of things. Here, these are the inputs to the GUI duct wing lofting command. One of the inputs is an airfoil distribution. That is a spline function which has 2 independent variables and 2 dependent variables. So you can see even the picture that I've drawn here of an airfoil distribution is a lie. Because if I think of the 2 independent variables as being, say, position around the airfoil as one, and then wingspan location as the other parameter, if I fix, say, a wingspan location, 50% span, for example, then what I have left is a function of 1 independent variable. I get a 2D curve. So that looks like a 3D curve there, and that's not a bad way to visualize it. But what it really is a series of 2D curves shown one on top of another. The planform curves, that's the leading edge curve and the trailing edge curve of the wing when you look at it from above. A twist schedule, it's important to twist airfoils depending on span location. So this is the twist schedule has 1 independent and 1 dependent variable. That's not a piece of geometry, it's just a function that I can plot the graph of. Thickness schedule, what is the thickness of each airfoil section? And then shear schedule. Sometimes you want to translate these airfoil sections up and down, often for ground clearance for a nacelle, for example. You'll see that the wings will be sheared upward near the engine installation and then maybe down a little bit near root and cord. And if you pass these 5 functions, spline functions, to the wing lofting command and GUI duct, out will come a new spline mapping with 2 independent and 3 dependent variables that gives you a lofted airplane wing. Okay, so even though thinking of the basic entities in the GUI duct system as functions rather than as bits of geometry as you would in a CAD system, even though that tends to make some of the engineers nervous, it's a very powerful idea to be able to do manipulations directly on functions. So the wing planform area calculation, if you look at this in the Boeing design guide, this will be a discussion that goes on for 6 or 8 pages. If your wing is a trapezoid, use this formula. If you have 1 leading edge break in the leading edge of the wing, then think of it this way and use this formula. Nowhere in those 6 or 8 pages does this integral, which tells you what the wing planform area actually is, appear. But you can write it down. You can figure that whole thing out. Well, one of the things you can do in GUI duct, because these are all piecewise polynomial functions, you can combine analytic and numerical operations together and do certain operations analytically. So the derivative of a piecewise polynomial function is a piecewise polynomial function. So you will get that thing. And again, all of this is going on under the covers. It's this very high-level GUI duct command here. The recurrence relation for differentiation of spline functions appears there. You can do the same thing here. And then again, products and differences of piecewise polynomial functions are piecewise polynomial functions. There's an algorithm called the Oslo algorithm because it was put together by Tom Lycke, who is Norwegian, when he had a little workshop in Oslo one year. It gives you the B-spline coefficients for the product of 2 spline functions. So that's all implemented in GUI duct, tucked away. And then the simple multiplication operation invokes that algorithm so that what you get is a B-spline representation of the spline, which is the difference of these 2 products. Then you apply the B-spline formula for formally integrating that, evaluate that at 1, and voila. You've got, to machine precision, that integral. Okay, but wait, there's more. Suppose we've got a curve. This is in 2D, and we want to project this point onto it. Well, you can apply all the things that you learned in first semester calculus. You can write down the difference between a point and the curve, dot product to get the square of the distance, differentiate that formula, and set the derivative equal to 0. So you do that exact thing in GUIDuck. Form the difference and the derivative of the difference, take the dot product of those things. F is now going to be a spline function with one independent and one dependent variable, and then you call this function here to get the zeros of that particular function, and it gives you those 4 points right there, and you pick the one at which evaluate the spline at those 4 points, pick the one which is the closest. And you'll also get the point that's farthest away and the whole bit. All right, that's pretty simple. Here's one that's a little bit more complicated on this rotor hub for a helicopter here. What about a horizon line calculation? Same kind of thing. Horizon line calculation, if I've got a surface, it is the locus of points at which the line of sight is perpendicular to the surface normal. So the partial of the surface map with respect to one variable cross the partial with respect to the other variable. Those 2 vectors span the tangent space, so the cross product will lie in the direction of the surface normal. And if I take the dot product of that with the line of sight, that's going to give me really one equation in the 2 variables which are the 2 independent variables for the surface map. So I expect to get a 1-parameter family of solutions back if I solve that contouring problem right there. And so I can just do that. I can formally differentiate the surface map, compute the difference, take the cross product, dot product, put all of this thing there. And now if I take the intersection of that with where the first component equals 0, what I will get back is a curve which is exactly what I'm looking for. All right. Developable surfaces. Let's take a look. This is a somewhat more interesting example here. Suppose that I've got a manufacturing operation, and I want to make sure that what I am modeling is a developable surface. A developable surface is one which has 0 Gauss curvature, so I can flatten it out. So you can imagine if what you are doing is bending something out of a pretty stiff sheet of aluminum, you want to be able to make sure that the shape that you're bending it into is a developable surface. This is even really true of composite materials, which can be very, very stiff, don't stretch much. That developable surfaces from the point of view of manufacturability are a really big deal. So, well, let's talk a little bit about developable surfaces. What's going on? Well, all developable surfaces are ruled surfaces. They can be thought of if I have 2 curves in space and I connect points from one curve to the second curve with straight lines. That will give me a ruled surface. So all developable surfaces are ruled surfaces. But the converse is not true. There are lots of ruled surfaces which are not developable. And the key distinction between them is for a ruled surface to be a developable surface, it must have a constant tangent plane along each ruling. So you know that one of the tangent vectors is the ruling itself. So what that really says is that the tangent vectors on the 2 curves that you're connecting with the straight line, those tangent vectors must be parallel. If they're parallel, then the tangent plane for the ruled surface will be constant across that whole ruling. If those aren't, you're now going to get a tangent plane which will which will linearly twist from one tangent vector to the other. Okay, so how can we take advantage of that idea? If what we're looking to do is to match up the points on the two curves in such a way that the tangent directions match, one way of going about that in GUIDUC is to say, all right, let's look at the hodographs of the two curves, that is, the functions which give you the tangent vectors, form the cross product of those two things, and then what I'm really going to look for is the cross products vanishing. I want the locus of points in the parameter spaces for those two surfaces at which those cross products vanish. So if I have arranged things so that the first point on the first curve and the first point on the second curve, that those tangent vectors match, and let's say the ones match for the endpoints of those curves, then as the curves wrap around, I can find such a correspondence. I'm really going to be able to get some curve. If I think of my UV space here, which is the preimage of this, going from the point 0, 0 to the point 1, 1, I can find some curve that goes from the origin to the point 1, 1, each point of which will give me in UV space the corresponding points on the two. I can do all of that in GUIDUC right here. Differentiate, take the tensor product, find the zero set, and then all of this is a way of subrange is an old don't ask. It's a non-mathematical word that means composition of functions. I'm going to, what I'm going to get from this intersection curve is u and v as functions of t. If I now compose my first curve with the u component of that function, my second curve with the v component of that function, I'm going to get c1 of u of t, and I'm going to get c2 of v of t, and now as a function of t, I've got all the right points lined up. If I now simply take the ruled surface between those two compositions of functions, voila, I have a developable surface, and it's developable by construction. Now, take a step back and look at, I mean, this is just 9 lines of GUIDUC code right here, and we've accomplished a lot. Because if I now make my two input curves parametric curves, I can vary say the design parameters that construct those two curves. I now have 9 lines of GUIDUC code that give me a parametric family of developable surfaces, so that I now could put together a design optimization problem, varying the input parameters of those two curves, doing an optimization-based search for the right design, where every single design that I am looking over satisfies this developability condition. I've imposed a really important manufacturing constraint into my problem in a way in which the optimizer doesn't even see it as a constraint, because my geometry construction process is giving me this manufacturability really for very little, at least in terms of coding it up. All right, let's look at another interesting problem right here, the spar location problem. One of the things that the aero guys are always wanting to do is to make the wings thinner and thinner and thinner and thinner, because you get better aerodynamic performance characteristics with thin airfoils. The structures guys, on the other hand, they actually need to support the wing and the fuel and all that stuff. They want these great, big, thick I-beams running down. If you could have one 3 stories tall, that would be even better. I'm actually going to have time for that. How many of you, I know a couple of you already do, why wings are swept backwards on, why instead of the wings sticking straight out, they do this on it's a really wonderful trade-off between aerodynamics and structures. If you sweep the wings back, imagine that you've got a circular airfoil so that the wing is a cylinder. If the wings are sticking straight out, the thickness relative to the chord is 1. So it isn't particularly good aerodynamically. But if I take that nice big thick wing and sweep it back, as I now take cuts through that cylinder, they become more and more elliptical. So aerodynamically, the wings are getting thinner and thinner and thinner as the wings are swept back, even though structurally I haven't changed very much. I've got the, so this was an idea that folks who went to Germany right after World War II, the Germans had come up with this idea. It's one of the things that came back from the war. And so you see swept wings appearing as early as 1946 and 1947. But I digress. So what the structures folks are wanting to do is to figure out where in this wing right here to stick a spar. And they would really like to stick it in the maximum thickness location. So how am I going to do that? Well, imagine I have a wing upper surface and a wing lower surface. What I want to do for each span location is to locate the place where the tangent vector for the upper surface and the lower surface are parallel to each other. If I can, kind of as I've drawn right here. So in particular, when the tangent vectors for the parameter for the upper and the lower are parallel to each other. So let's just go ahead and replace the upper and lower surfaces with the x and y components of the original surfaces plus the slopes. The change in z over change in x, change in z over change in... If those slopes match, I will have found the location. So here is the GUI duck code for that. HatSurf right here is a little Python function that I have written that takes a wing upper surface or a wing lower surface and constructs from that the thing that replaces the z component of that surface with the slope, the fore and aft slope of the section of the surface in those two places. So I write my little procedure right here that constructs these hat surfaces. I call that procedure on the upper surface of the wing, the lower surface of the wing, and then I intersect these two hat surfaces. Heaven help the guy who tries to think of these hat surfaces as surfaces in the sense of airplane geometry. I mean, they're purely mathematical objects. But once I intersect those things, then grab the curves and construct the ruled surface between the corresponding curves, I now get a spar located inside this wing that is as deep or tall as it can possibly be. Okay, we'll do one more. Suppose that I want to solve a machining problem. One way that that's typically done is to, you have a cutter and a surface, and the cutter, imagine I've got a cutter that looks like this. It is a spherical end mill. And what I want to do is to drive the cutter along that surface in such a way that I've got tangency contact between the cutter and the path along the surface that I'm driving. One of the ways in which tool paths are defined, though certainly not the only way, and I mean there are lots and lots of different ways, is to take a planar cut of the surface, and then if this is a 3-axis milling machine, then as I drive the cutter along that planar cut of the surface, I want to maintain that tangency. So let's take a look at what we've got going on right here. Here is the equation of the plane. This is some fixed constant n. if I take the dot product that n is the normal to the plane that I'm using to cut the surface. So here's the equation of the plane. And so the tooltip center, which is it's the center of the sphere of the end mill. This is, in fact, the point that you typically need to program to a machine tool. You need to describe that path to the machine tool, and it will. So we need a mathematical representation of that path in order to do machining. So that path has to satisfy what? Well, the distance from, that is the vector from the tooltip center to the surface that I'm machining, that vector has to be perpendicular to one of the vectors in the tangent plane. In fact, it has to be perpendicular to both vectors in the tangent plane. The distance from the tooltip center, squared anyway, has got to be equal to the square of the cutter radius. And the plane has to be the desired plane. So let's think about this right now. I've got the two parameters u and v that give me points on the surface. And then I have the three values x, y, and z that describe in space the location of the tooltip. So I've got those 5 variables in play, and I have these 4 equations right here. So again, I expect a 1-parameter family of solutions to these 4 nonlinear equations in the 5 variables. And so what I ought to get, if I parameterize that curve that wanders through 5 space, is u, v, x, y, and t, all as functions of some other parameter, t or tau. And as I look at that path, that trajectory in 5 space, I get not only the 3 components of the tooltip center, but the u and v, the fourth and fifth things, tell me what the corresponding point on the surface had to have been. I can set all of this up in GUIDuck in just a few lines, describe these things, call the contouring function, and it all pops right out.
How is the system solved?
That's a subject for another day. I've got a 2-hour talk on solving contouring problems. The basic idea, if I'll tell you simply, if you've got a nonlinear system, f of x equals 0, where f is a mapping from Rn to Rn minus 1, so that you have one fewer equation than you have independent variables. So you write down f of x equals 0, and then you attach to that x prime dotted with x double prime equals 0. That will regularize the parameterization. And in fact, it will give you an arc length parameterization of the 1-parameter family. And so that solves very beautifully with a spline collocation-based approach. And if you find either both endpoints, you can solve that as a boundary value problem, or you can find one endpoint and a direction and treat it as an initial value problem, and all of those things will work. And if you choose a 4th or 5th order spline, you get this really lovely high order convergence to the whole thing. Unlike most DAEs, this thing doesn't exhibit the typical loss of order of convergence. This particular DAE is exceptionally well behaved, and you can by taking this kind of a numerical approach to the thing, you can dial the accuracy on this up easily to 12 or 14 digits. Okay, I'm going to stop there. There are lots of, well, and you got one hint of it right there with there are some
like conservation of difficulty. But so what can you give us a hint of, I don't know, you mentioned
What sorts of things are under the hood?
Well, what did you use to create all that? I mean, is there some symbolic stuff also in addition to, typically numerical, or?
It's just been one of these things. There has never been, the Geoduck is sitting on top of a whole library of C code at Boeing called the Spline Toolkit that Dave Ferguson started working on in 1978, and I showed up in 86, and we kept adding to it. And it's one of these things where you get a little project and you add another grain of sand to the pile. And you know, after 20 or 25 years, you really get to have this lovely pile of sand that does all kinds of pretty cool stuff. Eve.
Part of what you had on the hood, you described very nicely an article in Science Review some years ago. Remember that?
That was, yeah, the contouring article. That was the very answer to your. Yeah.
Science Review.
There was a Siam Review article that.
So my question is, since there seems to be a lot of interest, have you considered writing another article for Science Review on Geoduck?
I haven't considered it, but
Okay, sorry.
but maybe it's time.
Is this code for sale or free or just used?
No. That's the short answer. But I'm happy to talk about it. Randy.
Is it using the grid refinement, or grid generation for solving aerodynamics problems, for example?
It is, and there are some, as the surfaces together, I mean, there are just some neat things for automated grid generation in there. I know one thing will take a network of surfaces that are stitched together in potentially some topologically complicated way and sets up a whole big linear programming problem designed to match the number of points on each of the edges so that you get this really lovely quad mesh out of the whole hodgepodge in the end. And there's, well, as we've said, I mean, you work on something for 30 or 35 years and there's some neat things there. I won't claim that we have solved the automated grid mesh generation problem by any stretch of the imagination, but for things that we have done before that are like things that we're going to continue to do in the future, you can capture a process. And so for something like a conventional jet transport, we can go from airplane geometry to CFD mesh in a couple of minutes in some cases. Don't change the topology of the airplane very much or it won't work. I mean, this is not a complete solution, but if you are exploring a family of designs where you can count on certain, the way certain things have been modeled to not change too much from one instance to the next, you can achieve quite a lot in terms of automation.
Any more questions? Okay, the last question for you. Where's that Chinese character?
Let me see if I can find it for you and email it to you. I mean, I've got it on a slide that I didn't put in this particular representation. And if you look up Geoduck at Wikipedia or someplace, it will show you the Chinese characters that describe this as it's a Pacific clam. So the Chinese and the Japanese and then the Native Americans all knew about this clam when the Europeans didn't. The word Geoduck is spelled in this ridiculous way. It is a Nisqually Indian word that means dig deep, which is what these clams do, and they dig very, very fast. The English speaker who transliterated Nisqually and several of the other was just a horrible speller. And so you find words like gooey duck and hundreds of others just really, really butchered in terms of their transcription into English.
I have it on an app here. Sean Baba.
Show it to her.
Okay, we'll do it later.
Okay.